I've always been fascinated by unconventional engines.
Oh yeah.
And recently I stumbled upon a few people on YouTube who had built air engine entirely from 3D printed parts. What surprised me wasn't just that they worked, but actually how well they performed. One guy even managed to attach his homemade air engine to a model airplane, powered only by two 1.5 liter plastic bottles at 7 bar. Incredibly, it keeps the plane airborne for nearly 90 seconds. That project sparked an idea I just couldn't ignore. One of the biggest challenges with these 3D printed engines is achieving airtight seals and reducing friction. Some builders struggle to fit 3D printed parts together perfectly to get good compression, but I had what I thought a brilliant solution.
Oh, that's hot. That's hot.
Some new glass syringes. In my humble opinion, this could completely solve the sealing issue. Plus, the low friction of glass pistons sliding in glass cylinders seemed like a huge advantage. Of course, there was one big downside I choose to ignore. Glass isn't exactly the most durable material for the motor. But at that point, my optimism had kicked into overdrive. I was so convinced of the benefits that I completely overlooked the obvious risks. Fueled by enthusiasm, I started designing the first version of my air engine using CAD software, eager to get it printed as soon as possible. Now here's where it really hit me. I was working with an old 3D printer that had seen better days. The print quality was mediocre at best, and the heated bed was warped beyond belief. I had to jerry-rig it with some wire and tape just to keep things somewhat functional. Well, after glancing at 3D printer prices and then at my bank account,
It's pretty difficult to put into words how disgusted I am, how depressed I am.
but despite the constant setbacks, I pressed on and got a brand new 3D printer, because I was determined to see the air engine come to life. Designing the engine was one thing, getting it to run another. For the valve mechanism, I did what any resourceful DIYer would do. I borrowed the concept from another YouTube project. The design was simple: an aluminium pin attached to the piston pressed against a small ball when the piston was at its uppermost position, opening the air intake. Thanks to gravity and complicated bit pressure differential, the ball would fall back into place, sealing the intake. As the piston moves down, it opens the exhaust ports, and the cycle repeats. To my surprise, the first prototype actually worked, at least in front of the camera. It ran for a few glorious seconds, but shortly after, the camera stopped filming and the engine refused to start again. Determined to figure out what went wrong, I relied on my favorite problem-solving technique: change something and see if it gets any better. Not the most scientific method, I admit, but it's surprisingly efficient. Sometimes. So first, I tried to increase the piston stroke length. That only made things worse. Eventually, I realized the engine lacked the momentum needed to overcome the compression phase. It simply didn't have enough flywheel effect to keep spinning through the tough spots. So I attached a large carbon propeller to add rotational inertia, and that helped stabilize the engine performance. But new problems emerged. Ironically, after spending so much effort optimizing for high compression, I discovered that too much compression was now a problem. The engine kept blowing itself apart, literally. The crankshaft snapped off during one test, and in another version the entire housing shattered under pressure. It was both frustrating and absurd, designing an engine for maximum compression, then fighting that very compression because it's too much for the materials to handle. Surprisingly, the third version of the engine worked quite well. It managed to produce up to 400 grams of thrust at 7 bar of pressure. For the video demonstration, I kept the pressure lower around 5 bar, which is still delivering about 300 grams of thrust. It wasn't perfect, but it was a significant improvement over the earlier prototypes. Encouraged by this success, I started planning the next version. This time my goal was to build something smaller and more compact, light enough to mount on an actual model airplane. I have already ordered a small glass syringes and begun designing a lightweight base that will hopefully allow for flight even with a relative weak engine. If there is one thing I've learned from this project, It's that optimism is both blessing and a curse. My enthusiasm pushed me to experiment with unconventional materials like glass. So what's next? More prototypes, more testing, and much more broken syringes. But that's the fun of it. Thanks for sticking around. I'm excited to see where this journey leads.